Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right, welcome everybody.
We are live on internet time.
And welcome to another episode of Ask Us Anything about electrochemistry. Neil, do you want to say anything to disarm these people before we just go straight to the chase and answer echem questions?
You can't go straight into the chase. You gotta warm up it, and get loose and funny and make it silly, and everybody's sort of happy to be here. Do some of those calisthenics you used to do in like first grade. You do the arm circles and you go back.
Oh, I do those. I do this for practice.
Is that real? That's not real.
The little arm circle.
Yeah, the arm circle thing. That's not a thing. I mean, people do it. Like,
yeah, people do
7-year-olds do it in gym class, and that's not real warm up.
It's part of a warm up.
Have you seen?
It's a fraction of a warm up.
Have you seen a professional basketball player or a hockey player doing arm circles at mid-court or mid-ice before the game to like get psyched to dunk the ball? That's not a thing. They do like real stretches.
They use real stretches.
Like,
what are real stretches?
You do some of these with your arms over your head, or you.
Wait, why is that a real stretch? But this is not a real stretch.
Because your arm is moving.
Because my arm is
supposed to be static. I am not a sports scientist, and this has all been a huge waste of time. So you're welcome, everybody.
It's all right. We did just have a question. Some questions, comments that just came in.
Yes.
I don't know. Should we just get to those right now?
No, I want to answer Dilly's question because
right,
technically I believe it was first. So we're gonna.
Yes.
We always have so many questions. We very much appreciate everybody, and often as these things happen, there are questions that show up earlier in the week on this event, and we try to save them and make sure we answer them because you are permitted to ask us anything about electrochemistry, as the name suggests. And so Dilly asked us something about electrochemistry earlier in the week. So I will try to do my best to answer that now. And so it's sort of a multi-part one. I'll try to walk through answers as best I can here. So the first part was I modified the glassy carbon electrode surface for electrochemical analysis using drop casting of biochar suspension. I guess I'm not sure exactly what that is, but sounds like probably some carbon effectively. Like you can basically burn biological material and you get carbon. And I suspect that's what Dilly has done using nafion as a binder, but the surface is not stable. How to solve this problem? So I can't answer directly, but what I can do is just sort of detail some of the kinds of strategies, I suppose, that you would use for the drop casting method. So in general, drop casting is a technique where you produce a suspension or a solution, depending on the terminology here, of a catalyst. So in his case, I suppose it's a carbon, some kind of a carbon in probably water, but maybe alcohol as well sometimes, with some other kind of chemical like nafion, which basically acts as a binder, or I just call it glue. It basically glues the catalyst to the surface, and you have a disc electrode, usually glassy carbon, as is indicated here. Usually it's turned upside down, so the glassy carbon is pointed up, and you take a small pipette, like a 10 to 20 microliters of volume pipette, micropipetter, and you deposit a drop of your suspension onto that, let it dry. And then you have your catalyst that you can run some electrochemical testing on. Now, as it seems to be the case here, the surface isn't stable. So the bits of advice that I will say about this and in general for drop casting are, one is that you might need to tinker with the solvent that you're using. Okay, so first of all, carbon is hydrophobic. And so sometimes using a heavy water-based ink solvent is not ideal. The carbon doesn't maybe disperse all that well. Sometimes people will cut it with 25% isopropanol or methanol or some kind of alcohol. So sometimes that can help. Number two is the ratio of binder and whether you have a 1 or 2 step process. And so sometimes what you'll do is, as this person has, I believe, indicated, so they have probably, 10 milliliters of water and 15 milligrams of carbon and 5 milligrams of nafion, whatever the amounts are. I'm just making up numbers out of nowhere. But you add the nafion into it, and then you make the deposit. Now, sometimes that can be a poor, or I should say more difficult drop casting technique for the surface reproducibility and stability, as this indication seems to be that the stability is a problem. Because how do you know, for example, it's well mixed such that the nafion, which again, it's a glue, it's basically gluing and making sure there's adhesion between the glassy carbon disc and the catalyst that you're trying to suspend on the surface. So if that adhesion is not great, you will have a problem. The surface will not be stable. The catalyst might delaminate, fall off, flake off in solution, something like that. And so that can happen if, for example, there's not well mixed enough, there's not enough nafion well distributed such that when it dries, the nafion really kind of glues everything to the surface. So sometimes what people will do, in fact, what I did when I was in graduate school was a 2-step process. So I made a suspension with my catalyst, dropped it on the surface, let it dry. Keep the electrode inverted as it is. So it's basically just fizzy-sorbed, and then do a second deposition of just the nafion suspension. So what I would do is we would use, it's pretty common, you can buy from like a chemical supplier like 5 weight percent. I think it's weight to volume or volume to volume. I forget precisely, but it's like 5% nafion suspension in water. Dilute it 100 times, and so it's 0.05%. And then you drop the same volume onto your surface of your glassy carbon disc of that 100x diluted nafion suspension onto the disc, onto your already dried catalyst. That makes sure basically that the glue in the binder is like really on top and, in theory, really gluing and adhering your catalyst to the surface. So you might try that. The third part of this is just very simply that the suspensions of your inks, make sure they're well mixed enough. Whether you're doing 1 or 2 step, make sure it's well mixed. Sometimes you sonicate for a while. Sometimes sonicating with an ice bath can help. I don't quite know why. I haven't figured that out precisely yet, but for some reason, cold temperatures do sometimes help the getting the suspension of, like, I don't know, carbon materials or something mixed a little better. So sometimes add some ice cubes. I know it sounds kind of silly, but add some ice cubes to your sonicator like bath, and sometimes sonicate in that. Sometimes I would do, I had very stubborn catalysts. I would take like the pipetter and I would literally stir physically with the pipette tip my ink solution while it's sonicating. And be careful you don't get the sonication bath will spit sometimes from the sonication. Make sure it doesn't contaminate. Okay. But I would do that for a little bit to try to make sure it's like super well mixed and consistent. And so that is another thing that can help you with the stability and the consistency of your film. So I will leave it there. Those are just some of the kind of very general pieces of advice for drop casting that I can give you. And hopefully with some trial and error, you'll be able to work your way through, consistency. And it really does end up just becoming something where trial and error is required. Should I do the rest of them, or should we interrupt?
Either, let's see. So that was the
first part of.
That was the first part of the question.
Yes.
If you want, we can come back to it later.
Sure.
There are 2 questions really.
Okay.
I think some simple, some like not so simple. But Badminton Chennai is asking, under what conditions does Butler Volmer become Tafel? Which is I think your favorite thing.
It is my favorite. I should pull up my slides.
If you want to pull up your slides,
I'm gonna do that. Yeah,
that's helpful. But generally speaking, there's really like 2 conditions. I would generally say to start things off. It's when the concentration or the overpotential is one such that one of the sides of the Butler Volmer equation, whether it's the oxidation side or the reduction side, is missing. So you only have one half of the reaction. That simplifies things a lot. You also, the Butler Volmer equation also contains things like the heterogeneous rate constant, concentration, Faraday's constant. A lot of those things get lumped in. They're usually constants, so they get lumped into just one term that we'll call the exchange current density. So once you mathematically kind of lump those things together and then get a concentration that only describes one side of the reaction versus another, then it's easy for Butler Volmer to become a Tafel equation.
Like a magnificent transformation.
Yes.
It just morphs into Tafel. Yes. So to Alex's point, this is the Butler Volmer equation. And effectively the Tafel equation is half the Butler Volmer equation. And so what we are looking for is one of these terms to be able to be neglected, right? That is what leads you to the Tafel equation. When you can neglect one of these, we can then simplify the Tafel equation here and solve it for the overpotential. That is what the Tafel equation is. So as far as numbers are concerned, most commonly we use the example of 120 millivolts. So when the overpotential is 120 millivolts plus or minus, we generally consider it to be irreversible in one direction or the other. And the reason for that is I could show that. I've done this before. I don't have it pulled up at the moment, but I could mathematically, what happens is when this is 120 millivolts, what you have is current from the oxidation part and current from the reduction part, effectively. That's what these two exponential terms are. They're like the contributions of the current from the oxidation or the reduction of like a one electron reversible process, basically. Kinetic current associated with that process. And when you have an overpotential of 120 millivolts, you get effectively 99% of one and 1% of the other. So it's dominated by the oxidation or the reduction, for example. So basically we're looking to push the reaction in one direction irreversibly, effectively, or in a majority way. And so usually we say that that's 120 millivolts as a rule of thumb. And then we effectively get the Tafel equation from the Butler Volmer equation because half of the Butler Volmer equation is neglectable.
Yep. Yeah. I hope that answers your question.
Yes.
That's how.
See, that one doesn't trigger me because they're not trying to make a Tafel plot inappropriately. They're just asking under what conditions does this happen. So I get to talk about it.
Yeah, just mention that.
Yeah.
So we have a question, a comment from Abhinav. He says, "Hi, I've been watching your videos lately. Thank you for making all these videos. Practically everything you need to learn is available here. Thank you so much." That's a very, very nice comment. They also asked, does Pine Research have any equipment for studying PEM fuel cells or electrolyzers? What set of equipment do you recommend for fuel cell research? I have not done too much fuel cell research.
Right. For specifically full fuel cell research, we make potentiostats that can be used for that, but we don't make fuel cell hardware, for instance. So when you're testing a fuel cell, a lot of times what you have is two bipolar plates that press together on a membrane electrode assembly, or MEA. A lot of times there are gas channels in both sides. You send, like for a PEM fuel cell, you send oxygen on one side, hydrogen on the other, right? And those are connected to some either independent, you make your own, or you buy a test stand of some kind of station that regulates the gas flow and the humidity and the temperatures and things like that. Sometimes those can also do the electrochemical measurements. Sometimes you use a separate potentiostat to do the electrochemical measurements. So what Pine can offer is the potentiostats, for instance, to measure the polarization curves, impedance, the electrochemical metrics of a fuel cell, but we don't make the fuel cell hardware specifically ourselves. What Pine does make, I guess, that is critical for fuel cell research is we sort of think of it as half cell individual anode or cathode kinds of tests. So for instance, many people over decades have used our equipment, our rotators, our rotating disc electrodes, rotating ring disc electrodes, and bipotentiostats to study the oxygen reduction reaction, which is what occurs at the cathode of a PEM fuel cell, or the hydrogen evolution reaction, or which is the hydrogen oxidation reaction, which is the opposite of that, I should say, which is what occurs at the anode of a PEM fuel cell. And so hydrogen evolution, hydrogen oxidation, oxygen reduction, oxygen evolution, these are all reactions that are part of either a PEM fuel cell or a PEM electrolyzer. And those can be studied very, very nicely with a rotating disc electrode or rotating ring disc electrode. That is the equipment that Pine makes specifically. So that's often what you're trying to do, because let's say you are trying to study a fuel cell, but you really just want to, as often is the case, improve upon the cathode, because the cathode is the rate limiting step in a PEM fuel cell. That's why people are often looking at different supports, platinum and different catalysts for non-noble metals, or improving the noble metal distribution and things of this nature, getting a better activity over time, better stability, better longevity. These are the kinds of studies that people are doing. And very often you want to focus on just one side. And it's convenient to have a system where you can just study the cathode or just study the anode. You don't have to make a whole fuel cell every time. And so that's what we do as a company. And among other things, you can do other kinds of electrocatalysis and a lot of other experiments with a rotator and a rotating disc electrode. But that's one of the more famous ones, I suppose you'd say. So just to be clear, again, we don't make the full fuel cell hardware ourselves, but the equipment for doing a lot of these analytical studies is what Pine makes and does very, very well.
All right. Let's see. He then says, what was he saying?
Yeah.
Now, the problem with 3 electrode system is that the catalyst surface is occupied by, yes, generated gas wells. Yeah.
Yeah.
That's
It's tricky for sure. This is one of the biggest challenges of doing gas generation, oxygen evolution, hydrogen evolution, anything like that. When you generate gas, you're in liquid phase. So hopefully the gas moves away from the surface and doesn't disturb the electrochemistry, but very often it does. Rotating the disc sometimes causes the bubbles to fling away, basically. Sometimes not so well. Sometimes bubbles get stuck and your data can be noisy. You're absolutely right. This is definitely one of the challenges of doing liquid phase rotating electrodes or disc electrodes, or any almost liquid phase electrochemistry. When gas is generated, it can be tricky for sure. I don't disagree with your comment for sure.
All right, moving on. Now we can go back to some of these questions we haven't answered.
Everybody can ask questions at your leisure, but we do have a bit of time to get through some of the questions that were asked previously. So let me try to finish Dilly's questions here. So the second one was, how can the parameters pH, deposition potential, and deposition time be optimized before DPV? So it says, for example, pH 4.6, potential -1 to 1.25, time is 100 to 150 seconds. Recommend a smarter way. Manual is tedious. So the first general comment is, unfortunately, yes, doing these kinds of optimizations can be very tedious, and that's just what it is. I don't want to be the bearer of bad news, but I guess I will be, because frankly, dealing with experiments, especially like differential pulse voltammetry, or really any pulse technique, or even CV to a certain extent, but certainly pulse techniques, is a trial and error kind of process. No matter how you slice it, basically, you're going to have to tinker with parameters. Now, I guess I don't totally understand the context of this question, in a sense it's optimized before DPV. So I guess I don't know if you mean what should I do in preparation for doing DPV, or you mean the DPV parameters itself. And I guess I don't totally know. Also, 100 to 150 seconds is pretty long time for like a short sweep. So, one of the things, I'll just sort of draw a quick like waveform as an example, but DPV is a technique where let me get my drawing thing here. The waveform, for example, so the potential versus time waveform looks something like this. I kind of exaggerated a little bit.
No, I mean,
that's about right.
That's good. Yeah.
Yeah. So this is DPV. Okay. And all I wanted to point out basically was that we have a couple of properties, I guess you'd say. So for example, this property, these are supposed to be all equal, by the way. This is clearly not, because my artistic skills are not perfect. However, just pretend that these are all equal, right? All of these increments in potential. So this is, E increment, whatever. And then on the time axis, the distance between any two points of the same, of the waveform, this would be like the time increment. All I'm doing here is pointing out that you can get at what's sort of, in CV, it's very easy, right? The millivolts per second that you're doing is very obvious. In something like DPV, the effective scan rate is here, right? The scan rate you can think of as the whatever millivolts or volts per second. So it's effectively E increment divided by T increment. And the point here is that sometimes what you're defining is this time and this time separately. You're defining this increment, but you're also defining, this pulse height. So if you're not careful, you might inadvertently select what is sort of a really slow scan rate or a really fast scan rate, right? One way, for example, to do that is if you set really, really short times for these pulses, like, milliseconds or even microseconds. It's like you're going to have a super fast scan rate. Maybe you want a super fast scan rate, but maybe you don't, right? Consider that. Now, if you set these times to be multiple seconds worth, you're going to go the other way. It's going to take a really long time. And that's effectively like scanning super slowly. So consider, CV, we all sort of know or think about more clearly. So it's like, if you're going to pick parameters that wind up being the equivalent of like half a millivolt per second scan rate, it's like, well, is that really what you want? Maybe the pulses are way too long. You're not even getting the benefit of them. So some of the trial and error, cut down time, if you will, is to figure out what the effective scan rate is. And you might be able to kind of draw some conclusions from that. But to be honest, a lot of your job is to sort of iterate on these things for your system and see how well it does what you're after, which is usually isolating a peak from the background noise, right? So that's kind of what I wanted to say about the DPV and maybe effective scan rate as it relates to cyclic voltammetry. Is there another question?
We do get another question that came in. Can answer this.
Let's see. Oh, the last bit of Dilly's question I could probably finish was just recommending best courses and books. For detection using CV, EIS, unrelated. Yeah. Well, I mean, frankly, I'll brag about us. We have exactly where we are right now is this YouTube channel. Alex makes videos. You have a video on CV, a video on EIS, a video on Amperometry, a video on Warburg impedance, a whole bunch of videos on how potentiostat works. And then I also have a lot of webinars that are on our YouTube channel where I go through a lot of those topics as well. RDE, Kentucky-Levitch analysis, potentiostat operation, impedance, circuit fitting, a lot of different stuff. So we are doing our best, I suppose you'd say, to keep the pedagogy of electrochemistry pretty accessible on our YouTube channel. Our website also has some support articles and information like that. And then, the obvious answers like Bard and Faulkner textbook, of course, is sometimes it doesn't help with practicality. Maybe, the good theory, but it doesn't help you necessarily with the practicals, and sometimes the Mark Arism's EIS book we always recommend is a good one. Do you have any other?
Oh, I was just going to mention on the Pine Research website, we have support articles, but we also do workshops as well.
Yeah.
So there are a couple workshops that are coming up soon, and you can sign up to attend one of them. Gives you a little bit more hands-on experience. None of them deal specifically with electrochemical detection itself. Like some of these will go over like cyclic voltammetry, but it's not like a glucose sensor. How does the glucose sensor work fundamentally, or getting to like limits of detection?
But of course, if you do these workshops, you'll get to be in person with Alex, and you can ask him those questions in person.
Yeah, that's right.
And then he's obligated to answer you because he's right in front of you.
That's right.
You can't run away.
I can't run away.
Exactly.
That is true. That is true. So, but yeah, those are kind of my things. But yeah, that's right. Textbooks are good.
Yes. All right, we've got through those.
Yes, you got through those questions, which are good.
These questions, and there are some new ones live. So let's take a look here.
So we have a kind of two questions from Polychem, or one major question. What is work of a salt bridge? How can ions have the same velocity of a cation and anion? Potassium, ion plus nitrate ion have the same velocity in a salt bridge, but they have different masses. So the purpose of a salt bridge is to kind of complete the circuit, if you will. Salt bridges are used in a variety of different types of electrochemical situations, I guess I would say. So if I'm just going to share my screen just to illustrate.
Yeah, you're good.
I'm good. Okay. Sometimes you'll see this in like a textbook. You'll have one system, and then you'll have like another like solution. There's liquid in here. So there's some liquid in here. There's some liquid in here. There is an electrode on one side, and there is some kind of like a voltmeter or power source on the others, connecting them. And then there's another electrode. But then there is this salt bridge, which I'll demonstrate via green. You'll have a salt bridge in between these. So this is the salt bridge. This green guy, salt bridge. And what this does is it acts as a way, like you're going to build up charge. If one of these things is doing an oxidation reaction, let's say you have an electron, let's say you have one getting reduced, so you have a reduction reaction. Or actually, no, this would be an oxidation reaction. So you have an oxidation reaction here. And let's say you have a reduction reaction here. So, and this is your reduction. And so if you just had oxidation happening here and you just had reduction happening here, you would build up charge on both of these solutions. You would just build up a lot of charge here and here. But charge just can't build up by itself. There needs to be something that balances the charge locally. And so that's what the salt bridge is for. So you said you had a salt bridge that contains potassium ions and some nitrate ions. And your question, and so what will happen is as we lose electrons here because they're getting oxidized, you'll have NO3. Oops. You'll have you'll have a lot of NO3 plus start to migrate over to this side, and you'll tend to have more K plus go to this side because there's more electrons moving here. You're going to have more K plus here. So the ions in the salt bridge migrate to help balance out the charge. Now, your question was, why do these two have the same velocity or same speed, even though they're different masses? And I think you bring up a really good point. You bring up a very good point. Just by itself, something that's bigger shouldn't move necessarily as quickly as something that's smaller, and K plus is much smaller than NO3 minus. But I think we also need to think about speed and velocity in another in another context, which is the molecule get like. I agree that both of these will have different speeds if you were completely in vacuum and you just shot these two molecules out with the same amount of energy. You're right. Something that has, if it's the same amount of energy and one has more mass than the other one, then yeah, absolutely. One of them's absolutely going to be moving at a different velocity. But they're not. Like, they're surrounded by water molecules, right? There's all this like solution, there's all this like water all around, like inside the salt bridge, there's lots of water. So all these potassium ions, all these nitrate ions, they're going to bump into water that's along the way. So really, they're kind of diffusing. They're diffusing, randomly moving from one side to the other, but also you have migration. So yes, mass is not the only factor that's involved in the velocity or the movement of like ion from point A moving to point B. It's not just the mass of the ion, it's the charge, it's the size, and yes, maybe also on the time scale, on like really, really, really fast time scales, maybe this guy is actually faster. This K plus could move a little bit faster, but on the time scale, of charge balance, it's so fast that we actually can't measure that difference. It all appears instantaneous from our perspective. So that's kind of my comment about like the speed of ions, like the purpose of a salt bridge and the speed of ions. Why would one move faster than the other one? But in this case, they're moving at the same speed. Well, they all have to balance charge at the same time. So they necessarily have to move kind of the same distance at the same time. So migration and electric field effects also play a role. So hopefully that kind of answers your question.
Very good. All right, I think Tarun has a question. I'll try to read it. It's a little bit long here, but I read your Pine research documentation through. It was great. It was a great delve into electrochemistry. Appreciate that. It would be great if you can take CV and LSV graph current versus voltage, either in PEM fuel cell or PEM working electrode, I guess. Catalyst development, for example, ECSA and ORR, and explain the regions, double layer capacitance, ECSA, oxide layer formation, ORR. Thank you for the constant upskilling at RDE scale and single cell. So there's a couple of curves that I can talk through, I guess. I have a couple. Sorry, I was pulling up one other one. This is the one I wanted. Where is it? I have a platinum something or other. Is this the one? No, that's fuel cell. Hang on. I'm getting a curve to talk about ECSA. That's not it. I'm gonna fit, and it's gonna be amazing. Fuel cells. Is this the one? I have a lot of example data, so you have to pardon me as I find it. Here it is. Okay. Let me share my software. I have some data here to show you. So the first one, this is relevant to PEM fuel cells, but this is, I'll just talk through this a little, I guess, as you said, that this is sort of one of these common plots that have regions to talk through. So this is the platinum cyclic voltammogram in something like sulfuric acid, or just acid in general. And this is a very famous voltammogram, and the regions are effectively as follows. So the, let me do a thing, this probably helps, select points. So the points in this region here, okay, these are the platinum absorption desorption region. And so what we have is so this is, I guess, minus 0.312, just for example, the number you can see at the bottom. From here, if we start here and go negative, just imagine this region right here. There's typically 3 peaks for a variety of reasons, the surface concentration and a lot of other kinds of things. Sometimes you only get 2. It's just it's a mechanistic thing. Sometimes the mechanism is good or bad depending on the crystal facet of your platinum. There's a lot there. I'm not going to get more heavy into the interpretation, but the peaks, reduction peaks negatively in this region, our platinum adsorption. So this is platinum, like
Hydrogen absorption.
excuse me, platinum absorption, hydrogen.
Yeah.
Thank you. Yes.
Okay.
Hydrogen adsorption
Yeah.
on the platinum. So
On the
we write like PT-H basically. And this is where platinum is absorbing onto the, hydrogen is absorbing onto the platinum. Words are hard. Okay. And then on the way back, the oxidation, that's the platinum. I'm going to do it once right. On the way back, it's the hydrogen desorption region. I don't know.
I understand. We're just talking so much about platinum.
Every time I'm trying to say hydrogen, I say platinum. Good grief. Okay.
It's all good.
Yeah. So this region in aggregate is the hydrogen adsorption desorption region. And so on the way negatively, we are adsorbing hydrogen on the platinum surface. And on the way back positively, we are desorbing the hydrogen from the platinum surface. That's what that region is. Next in the curve is this magical region, which is the only place on this voltammogram where we have just double layer. This region is critical because what we do to get the ECSA is we effectively take this band, usually it's subjective, you're picking points in this region here because there's nothing, quote unquote, happening except the difference between the positive and the negative sweeps basically is proportionate to the capacitance, the double layer capacitance. So this middle region here, that's what that's for. And so what we do to calculate the ECSA very often is we get the surface area under the curve, usually of the time versus current data, and we can relate that to the electrochemically active surface area of our platinum catalyst. And then finally, there's a few things, right? As we increase the potential up to this region, we get the platinum oxidation region. Am I not on points anymore? Points. The platinum oxidation region. So there's an increase in the current. We get platinum oxides. I guess just surface sort of oxidized species. There's a lot of literature and stuff on that too. What are those? Is it just platinum oxide or there's some other processes people will talk about until you get to a much higher potential up here. And when you start getting the oxygen evolution reaction, usually we don't scan so high that this current starts to increase a lot. You'll get a lot of oxygen evolution as you push the potential further. And then finally, as we scan back negatively, we get this magical peak, which is the oxygen reduction reaction or the platinum oxide reduction as well. And so those are the peaks and the things that are occurring on your platinum CV, I guess, there related to the ECSA. And then I guess the only other thing was about polarization curve. So you were talking about PEM fuel cells. I guess this is another representation of that. But it's a different one than what I was just showing. This is a full fuel cell for a PEM fuel cell. This is an example polarization. This isn't the nicest looking data. I don't remember where I got this, to be honest. It's been a long time. I'll actually draw it. Perhaps let's be a little bit more accurate to what a real polarization curve is supposed to look like. Let's just pretend that my data looks as good as this data. What we usually have is with a polarization curve, we have the axes flipped. So now what we have is instead of current on the y-axis, we have current on the x-axis, and we have potential or voltage on the y-axis. And what we usually have is, let's say this is 1.23 volts, and this is 0 volts. The curve usually looks something like this. And then sometimes it is a little noisy at the end. But what we basically have is a region in the beginning. This is, we sort of call this the activation. It's kind of like the voltage has to be dropped a little bit before we start getting any current out of it. And so that's just, we call that activation. It's sort of the energy required. I don't know if it's technically activation energy, the way we think of like the Arrhenius constant and things like that. There might be something to that, but this is just what it's generally called. And then as the current starts to increase in this way, now this is normally we think of a current going up as a peak, right, in a CV. And here recognize the axes are flipped. So the current increasing is moving to the right on the x-axis. It's kind of wonky. Your brain doesn't, if you're used to CVs, your brain might not like know what to do with that. But that's where the kinetic, that's like the kinetic, sometimes we call that the kinetic region or the kinetic, behavior when the current really starts to shoot out. And then for the most part, this whole region is relatively flat. It's the slope is relatively constant. So we call this the ohmic region, and it's the part where in the fuel cell where we have a easily measurable and direct relationship between the voltage change and the current change. So you can think of it as like Ohm's law, right? Think it's called the ohmic region. You can just imagine that V is IR. So it's like the resistance is relatively constant in this region, basically. And then finally we have mass transport or diffusion region. And by the way, sometimes this region in the middle here is called the mixed or transition region, like where kinetic and ohmics. This region might be like the transition. That's another term that some people will throw out. But mass transport or diffusion. So that's where when this shoots straight down, the current is not increasing anymore, but the voltage keeps dropping. And so we're reaching a limitation of a mass transport where we're effectively not able to get any more out of it. And sometimes it'll look kind of messy, and that's just, we'll have water crossover or sometimes flooding of the cell that can cause similar problems in the same way that gas generation on a liquid system causes problems. In a PEM fuel cell, you can have liquid flooding the system, and that causes a little bit of noisiness with your data sometimes too. So I think that's a good summary, I guess, of those pretty common current voltage, current potential plots, I suppose, specific to the PEM fuel cell and platinum and things like that. So follow up if you need any more info on those, and I can talk about. I see you asked about an EIS curve. We could try to get there eventually, I suppose. We'll try to go in order, I guess, or
I know Badminton Chennai, he actually redacted one question and then rewrote it a little bit later.
Okay.
But we can go to Abhinav's question. I'm not pronouncing everyone's name right. Is there a standard procedure for determining ECSA? I'm using a nickel foam electrode.
Well, the way is that I described is standard, but it's specific for platinum. Yeah.
For nickel, nickel is similar to platinum in some cases, but not exactly. And I feel like we get this question a lot about ECSA. There are many ways people calculate the ECSA that's not on platinum.
Yeah. There's no standardization that I'm aware of for any material other than platinum. And platinum is just the most well-defined, well-known, well-studied one. And the reason is that what I showed you just now, the area under the curve of current versus time gives you units of coulombs. It's charge. And the reason why this works to get ECSA is because I have the original paper. Sometimes I could show it, but you're not asking about platinum. I'm not going to waylay it. But the point is that some researchers like 50 years ago made painstaking measurements on different crystal facets of platinum, like 111 and 110 and stuff like that, for exactly the amount of charge associated with the hydrogen. I'm really having problems today. I don't know what's going on. My brain refuses to say hydrogen. Some researchers really painstakingly took the time, like they got a pure crystal of platinum and they set it up into a cell of some kind, right? And they got hydrogen in there, I guess, and they got it to adsorb or desorb, and they measured the charge like specifically associated with just that reaction. And they measured this, and there's different numbers for the different crystal facets, and the number that everybody knows, 210 microcoulombs per square centimeter, is actually technically an average of a lot of crystal faces. So there's some inside information for you. It's actually not it's an aggregate. It's an average. So even that's got some error associated with it, but it's still a tried and true method, which is that in other words, I'll bring it to nickel, right? It's like if you can find a paper, or you have the ability to, in like a super well controlled experiment. I know this isn't easy, perhaps, but find a way to measure the charge associated with some specific process on nickel, for instance. Now, nickel's a little trickier. It doesn't do this kind of thing. It oxidizes. Um, you know, it's usually used in alkaline media, and you'll have nickel hydroxide formation, nickel oxyhydroxide. There might be something you can do where you can measure an ideal situation. You know the exact surface area of it. You could measure the charge associated with the formation of some species. You'll get a specific number, like how many micro or millicoulombs per square centimeter, and then you can use that number as your similar reference. But again, I don't know anybody's really done that for anything besides platinum, and so there isn't really a standard procedure, unfortunately. I think that in most cases, by my observation and by my assumption, I guess, is that for determining ECSA for anything that's not the platinum 210 easy, procedure everybody does, you either do something like BET, which gives you the specific, like, meters squared per gram specific surface area of a material through nitrogen adsorption. That's just a physical, amount. And then you multiply by the mass and you get the number of, like, meters squared or centimeters squared or whatever. And that people will assume that physical surface area is the ECSA, because that's like, it's not perfect, right? It's certainly not perfect. It's problematic because some of the catalyst is like, there's a backside to it. If you do a drop cast, some part of your catalyst is not accessible because it's like the bottom of it that's attached to the disc. Like, how much is attached? These are all very unknown questions, and I guess the tricky thing is, I have not found consistent, I guess, publications or resources that details standard ECSA measurements on anything other than platinum that I'm aware of. And if you could do it, you might be very famous, but also you'd have to prove it works for every kind of nickel catalyst. You know what I mean? Like, it's really tricky, I guess. It's a hard proposition. I think that you're basically, most people's only recourse is to make an educated assumption that the geometric surface area, as best as you can calculate it, is the ECSA, or you just normalize your current to the geometric area and you note that it's like, you'd show current density like milliamps per centimeter squared. And sometimes people put like milliamps per geometric area. Like, you just in your publication, for instance, you are very open about its geometric area specific current, not ECSA area specific current, if you understand what I mean. So that's kind of my summary of that. Unfortunately, I wish there was a better answer, but I don't know of one.
All right. It's okay. So going on, we have this is the question from Badminton. He's asking, what formula relates thermodynamics and electrochemistry? Explain the different regions in the LSV and explain the importance of a KL plot, Kotecki-Levitch plot. So the formula that relates thermodynamics to electrochemistry, generally speaking, is the Nernst equation. And
this question was tailor-made for you.
Well, almost. It's like,
it's not quite.
The Nernst equation. So this is the Nernst equation. And basically, if you want to relate this, there's also even like more detailed like thermodynamic stuff. But I think it's like delta G is then equal to negative
NFE.
Yeah, that's right. And they do N and then F and then E.
Yeah.
And so this relates the Gibbs free energy, or the change in the Gibbs free energy, to the potential that is applied on your working electrode. So this is the general equation that people use when trying to relate the electrode potential or the redox potential to Gibbs free energy or the thermodynamics of the system. And then I guess I don't know too much about his next question. He wants to explain the different regions of an LSV, just like a CV. Like, is that
Well,
the?
there's no answer to that question. Is LSV on what?
Yeah,
You know,
LSV on what? So
the different regions of an, like I just described, the regions of a polarization curve or the platinum, cyclic voltammogram.
yeah,
But LSV is just linear sweep voltammetry. That's just a
that's just
method
the
where you,
technique.
yeah,
Yeah,
exactly.
you're just doing this. This is time, and this is voltage. That's the LSV technique.
Yeah,
But like it can create a whole bunch of different results
depending on what you're,
depending on what you're studying.
yeah.
Um, uh,
And then a
and
Kotecki-Levitch
and
plot.
then Kotecki-Levitch plot, which is this guy, right? So this is the Levitch equation
And the Kotecki-Levitch equation.
right here, and then this is the Kotecki-Levitch equation.
Mhm.
So the Kotecki-Levitch equation is very useful, particularly because of this. It's a method that allows you to determine the kinetic current, which is the current that does not have contributions due to non-Faradaic processes, not mass transport limiting. Um, it's usually done like when you have an RDE, you tend to have this kind of this S-shaped voltammogram. Kotecki-Levitch data is usually taken outside of like either the mass transport limiting regions. It's either the region where nothing is happening because the potential is not sufficiently high, or the mass transport limiting region where you only the measured current is only related to the limiting current from the Levitch equation. So the Kotecki-Levitch equation, where you get potential, you look at the potential um, versus, but you look at the current versus potential in this specific region allows you to generate a plot. And I believe it's one. I think it's the square root
1 over
of
the
the
square root
scan
versus
rate,
1 over the
or
square
sorry,
root.
the rotation rate.
Yeah, 1 over the rotation rate square root versus
Current.
1 over the current.
1 over the current.
Yeah.
And then when they do this, you end up getting plots that look like this. I'm sorry, I don't draw like slopes very well.
Yeah, something like that.
But basically the idea is for this expression, the the y-intercepts here are equal to the IK. And this is and when you think about it, this is 1 over the rotation rate, which means at this point here, you have a quote infinite rotation rate. Like that's crazy, right? So something that normally has a very finite limitation, you can only rotate something so fast. We have extrapolated it mathematically to the infinitely fast rotation rate, which means that the current is only associated with kinetics. There's no mass transport limitation. So this is really useful because you don't have to go to super fast scan rates. You don't have to, do either high frequency EIS. This is another way to extrapolate the pure kinetic heterogeneous rate constant or exchange current density for a redox reaction. Of course, it all depends on making sure that this all works and applies and your system is sufficiently slow. Otherwise, you're not going to get good data. But yeah, that is the importance of the Kotecki-Levitch plot, because that's what you asked for.
Yes.
Importance, not everything about what it is,
That's
but
right.
it's important.
Just why it's
trying
important.
to answer some of your questions.
Yes.
Okay.
So it looks like Taran had also followed up. I talked about the LSV and the power curve and things, or not the power curve, the polarization curve. Talk about EIS curve. So a typical EIS curve for a fuel cell can vary depending on what potential you're at, or what voltage the cell's at, what's going on. But let's just say that a very general say Nyquist plot for a fuel cell might just kind of be a Randall circuit, something like this. And so basically, in very brief here, what we have is if this is the origin 0 here, right? we can make a lot of assumptions on the Nyquist plot for the real axis, the x-axis basically. And so this distance right here on the x-axis between 0 and where the data sort of starts at high frequency, this is your ohmic or uncompensated resistance. It's called R0 or sometimes R ohm. This basically will have a semicircle kind of a shape, and the next resistance is basically the width of this semicircle. That is the charge transfer resistance of the process that's going on. If you have two semicircles, you'll have two charge transfer resistances. And then basically we have this kind of feature that tends to occur, which is usually 45 degrees. And this is what we call Warburg impedance. And then this can be the case where it goes up at a 45-degree angle. This is basically diffusional effects. At the low frequency, on the right part of my Nyquist plot, I have the effects of diffusion. Sometimes it does that. Sometimes it curls down. Sometimes it shoots straight up. There's a lot of different reasons for that. I mean, I'm not going to talk much more about it because there's a lot of possibilities. I'm just sort of giving you a general interpretation of EIS data. And the circuit that is usually used to describe this would consist of this ohmic resistance or uncompensated resistance, followed by a Randall's element, which has a resistor and a capacitor or a constant phase. I'll just draw a capacitor. So this is the double layer capacitance. This is the charge transfer resistance. And then we have a Warburg diffusion mass transport element here. And so this is a Randall's circuit. That's the sort of typical kind of circuit that's used to define this type of behavior that you do get quite often with fuel cells and other kinds of systems.
Okay, so the next question that we have a bunch of questions, which is great. Sonia is asking, how can I calculate the band gap of the material from CV if it has two reduction peaks? So you generally speaking, you can't determine the band gap of a material using electrochemistry or with cyclic voltammetry. You really do need to use spectroscopic techniques. It's very complicated to, I think it's very complicated to try to convert between the energy, that is what the band gap is, and the potential that you are applying between these two. Now, your system, you said, has two reduction peaks. I would need to know a little bit more about the system to understand why you get two reduction peaks. Do you also get two oxidation peaks? Is it a reversible process? So yeah, unfortunately, you cannot determine the band gap from CV just by itself. And I don't know about necessarily if it has, like, when it has two reduction peaks.
What band gap measurements, I mean, we've been through this, we've talked about this a handful of times before. I feel like, aren't band gap measurements mainly like spectroscopic?
Yeah,
like,
yeah, they're usually light-based.
Okay, yeah, I don't believe, and I could be wrong, but I don't believe there are any known electrochemical methods for determining band gap.
Yeah.
You can, let me think, like even like Mott-Schottky, you get like flat band potential, it doesn't measure the band gap. It's not, it's not something, in fact, you sort of have to have a band gap to be able to do Mott-Schottky in the first place. And then it's not measuring it. It's something, I mean, you could potentially say like my Mott-Schottky results are terrible, therefore my band gap isn't good, like, but it's not a quantitative measurement, so to speak. I'm just thinking outside the box.
Yeah, no.
It's not like a measurement of the band gap.
Yeah. If you,
like, the best you could do is you do Mott-Schottky and your results are awful.
Yes.
And it's like, okay, well, this must be a conductor.
Yeah.
So my band gap is small, but that's not real.
Oh, yeah.
That's not much.
That's not
I'm
like
stretching
the
here a little,
measurement
to be
of
honest.
the band gap. Yeah, you really need to use light to determine it. You're trying to excite an electron from a valence band to the band gap. Everything else about electrochemistry is like adding or subtracting electrons from those bands. It's not moving it in a way that allows you to make a calculation. And And so let me just see. He has a question. It's like, so, says using spectroscopy to get band gap. And then he's talking about electrochemical band gap, which is the difference between the HOMO and LUMO.
I don't know that that's different, is it? Like that's the
Well,
same thing.
so the HOMO and LUMO is usually referred to, it's like a molecule. So you have a molecule in solution, and that molecule has a HOMO and LUMO.
Yeah.
But you also can't determine that either. We generally say that you're ejecting electrons into like maybe the HOMO or removing them from the LUMO when you're doing electrochemistry. But the problem is this. So
I also don't know that like is the band gap is the band gap. Is there a difference between an optical and electrochemical band gap? Because I don't know that that's a thing. Like the band gap is just a fundamental thing of a material.
yeah.
I don't know that there's differentiating, and I might be wrong. There might be plenty of literature or something about that. But anyway, proceed.
No, yeah, no. I'm just saying when you have, let's say you have a pure conductor. Well, actually, no. I'm gonna let me just go. So you have molecular orbitals, and then you have a HOMO, which is the highest occupied molecular orbital, and then you have the LUMO, which is the lowest unoccupied molecular orbital, and they have a bunch of other stuff. And let's just say these are filled, and there's a bunch of stuff below, and they're all filled, and there's a bunch of stuff here, and they're all not filled. And when you do electrochemistry, you are either taking a molecule out of the HOMO or you're adding a molecule into the LUMO. But here's the problem.
Do you mean an electron or a molecule?
An electron, sorry. So
Okay.
an electron. Sorry, I'm talking about electrons here.
Okay. Yeah.
Yeah. It's like I can't say electron.
And I can't say hydrogen.
No, you can say. Yeah, you can't say.
I can't say hydrogen.
You can't say hydrogen.
I'm talking about platinum absorption.
Platinum.
That's right. There's little platinum molecules absorbing onto stuff. That's how it works.
That's how it works.
Goodness.
So so now these are all discrete energy levels in the HOMO and the LUMO. When you have things in solution, you actually get what's referred to as a density of states. I've talked about a little bit. So, and this is just because I don't draw these.
That's
very well.
good. That is actually exactly. Yeah.
Density of states. So some of these are like filled because this is like your HOMO, and this is and this is let's just fill these red so that you know that they're kind of empty.
Yeah.
So that they're different.
Yeah,
and there's a density of states because you're in solution, because the molecules are because the molecules have a big distribution of energy. They have solvation energy, they have different electronic configurations and stuff like that, molecular configurations. That's why whenever you do CV, you get something that looks like this. You get a CV as opposed to something where it's just like, boom, I get like a spike, and then as I go back, it's like, boom, I get this like spike or something like that, right? It's not discrete energy or discrete potentials. It's actually ends up being a distribution. And there's of course other factors that go into the shape of the CV. There's mass transport, stuff like that. But yeah, when you have like a metal electrode, this is the Fermi level energy of the system. You get electrons to go here and here as you move. This is energy. Of course, you move a potential with your potentiostat to kind of move these things up and down. And I'm not going to get into electrochemical potential because everybody hates that.
Everybody hates that.
I mean, I could get into it, but
it's kind of a lot.
It's a bit of a lot for now. But Sonyu, I hope that helps. And of course, if you have further questions about that, more clarification, let me know.
So it looks like Wong is here.
Yes, Wong Kai. I was going to answer all your
there were
questions
some questions
about
and
electrometers and stuff.
Here now, so we'll cut out the saved ones if you want to start digging into these. We had your questions saved. We were going to get to them as soon as we could.
You showed up live.
But now you're here, so we'll just directly answer your questions. I'm going to delete them in the save things if you want to start digging in.
Yeah. So, so this first question, Wang Kailai, is can you explain why things like self-assembled monolayers coated on an electrode surface will cause the peak separation in the CV to increase, for example, in ferrocyanide solution? So when you add a self-assembled monolayer to, say, gold or some other type of electrode, well, it's only gold mostly, you just increase the resistance. In a way, you're making it so that the applied potential is not the potential that you're actually applying, if you will, to the electrode surface. There's an image I usually like to share that relates this whole thing. And that is just thinking about the electrode surface as kind of a, well, Neil put this up. So you have solution resistance, which had RO, and then you have charge transfer resistance, and then RCT, and then of course there's a Warburg thing here, and then you have your CDL, your double layer. Now, what happens is, as electrochemists, we want to do all of our chemistry here. We don't want this to happen, but we necessarily have it. This is a necessary evil that we have to deal with. The fact that we literally can't get our reference electrode probe any closer to this interface, and this is working. But remember that this is a series resistor. So when you have gold on your surface, let's just say this is gold, and I'll try and make it gold in color.
Yeah, he seems to have already figured out where you're going here. He says, "Oh, it'll be part of solution resistance."
It'll be part of solution resistance. That's right.
Finish your thought, but I think you've already led him to the eureka moment.
Yeah. The eureka moment. And so you're going to have more resistance, right? Because you have the style on the surface. And what that does, which I find to be interesting and fascinating, is when you do cyclic voltammetry, because it still doesn't say like, okay, well, there you have more solution resistance, but why do you get peak separation, right? Your peaks are more like, they're more like this and this, as opposed to being, more here and here. The peak separation is farther. So the reason why is because the applied potential at this point is made up of IR drop. So even though you think you apply like 1 volt, you're actually applying something like 0.5 or 0.7 volts or something like that. You're actually applying a lower potential. That's what you're actually applying on the electrode. So that means you have to go to a higher potential on the oxidation side, and you have to go to a lower potential on the reduction side to get back to the appropriate potentials where the reactions occur. So that's why there's this like separation. So yes, but you got the picture. I think you understand why you get peak separation in particular. Okay, and then we'll try to answer as many of your questions as we can. So this is related to your question, on the how a potentiostat works video. The electrometer, you have the reference, you have the working electrode, and I believe you were saying if you compare bare electrode with a gold electrode coated in a layer of thiols, which will be highly resistive, which will affect the potential applied on the working electrode. I think maybe we necessarily answered this already. Right, that's what
the added resistance eats away at the applied potential. It doesn't impact the electrometer's ability to measure the potential difference. It's just that the potential at your working electrode is impacted heavily by the IR drop.
Yeah.
right, by the solution resistance.
Yeah. So I think because I remember when you asked the question, maybe I misinterpreted it as like, what happens if you made the reference electrode gold with a thiol? How would it
Mm,
measure the potential? I don't know if that was exactly your question as I just go through your questions now, but
I think you probably
but
answered that.
I think I've answered. Of course, leave a comment. You know, we're happy to talk. And then his third and I think last question for now is also trying to understand what causes the potential drop across the double layer and its relationship with the double layer thickness. Would you mind talking about in the next? Oh, which is now,
Just now.
which is right now. Yes. So, all right. So the electrical. Let's see. So what causes the potential drop? So let's talk just a little bit about the double layer, I guess. So let's just add a slide. So I'm trying to think about when you say so the electrical double layer, which is always a pain that we always think about and deal with.
Hmm.
I'm gonna draw this a little differently, and what I like to do this, let's see if this works. So let's make this we'll make this positively charged. Okay, that should be enough. And then we'll just make it a little bit bigger, and we'll make it we'll keep it we'll make these red. We'll make these red so that they're easy to see. All right, so we got positive charge, a working electrode, and this positive charge, generally speaking, attracts these negative anions towards the electrode surface. You, of course, have other things like solvent molecules, those little dots, things like that. So that's, solvated. Some of these guys are bonded directly to it. Some of them, the solvent molecules bonded directly to it. But overall, you end up getting a situation where you have net positive charge here and then net negative charge. And then let me go back, which is a quote capacitor. And so if I go back to the question, I'm trying to remember what causes the potential drop across the double layer. The potential drop across the double. Oh, okay. So maybe.
I mean, the
Maybe. Okay, I think
Q is equal to C times V.
Yeah, so I think this is. Let me actually share a slightly different useful things. This is from. This is from Bard, and no, that's the same thing. Here we go. And I think it's one. All right. So this,
Yeah,
I think,
the plot of the potential drop by
yeah,
distance, basically, it's pretty fast, or it's pretty steep. But
yeah.
that one.
Yeah, this one. So if I share this, and there are many ways to kind of think about it. This is from electrochemical methods, fundamental. It's Bard and Faulkner. So this is the.
It went away.
Went away. Oh,
Not sure why.
that's weird. Okay, let's try sharing.
I think when you enabled editing, it like redid the window.
Oh, okay.
Yeah.
Okay. All right. It redid the window.
Yeah, there you go.
So I think this is what you're talking about when you talk about the potential drop, right? So this is from Bard and Faulkner. This is kind of the same thing, like the image that we have of the electrical double layer. You have your metal, you have your ions. So the potential drop across the double layer is effectively due to you have a potential of the metal. So your metal has a potential and your solution has a potential. And so when you put two interfaces together, they quote equilibrate based on, and God, I wasn't planning on talking about it, but you know what, you guys always, you forced my hand. You forced me to talk about good old electrochemical potential. So, so in your system, electrochemical systems have try to get the electrochemical potential
dreaded
to
electrochemical
be equal
potential.
to one another. So this is what happens, for whatever species, so this is the, of the metal, and the electrochemical potential of the solution, which is made up of all the species in the solution and all the species, in the metal. And this can be thought of as Fermi energy as well. You can think of this as Fermi energy. They're very much equivalent. So systems, when they're placed in contact with each other. So let's say you have so just think of it this way. You have these two interfaces. One of them has an electrochemical potential that's here. One of them has an electrochemical potential that's here. Sorry, these are bars over it. When you put them in contact with one another, right, you have this guy, which is here, and then this guy, which is here. They equilibrate. They come together. But they come together by some of the energy from one going up and some of the energy going down to lower the free energy. And to do this at an electrode interface, it necessarily requires like electrons move here and ions move here. So potential is the electrostatic potential, right? So this creates an electric field. That's what this is. This potential drop is the electric field across this interface that forms the electrical double layer. So that is the answer as to what causes the potential drop across the double layer. Now, that actually doesn't have anything to do with electrical double layer thickness. That's just fundamentally what causes it. What adjusts or changes the electrical double layer thickness is the ion concentration. So no, that's the wrong thing. It's the ion concentration. Actually, that is actually kind of the right thing. So we have this thing. So you can have a situation here. You have phi, and then you have phi solution, and you have phi metal. So what makes this like go like this versus like this versus like this? What changes from distance, because this is distance. What makes this distance different? And the ultimate thing that does is electrolyte concentration. And electrolytes, just make it concentration. And so why is that the case? Well, if the charges need to be balanced, the field, like an electric field, exists because you have unbalanced charge. If you don't have a high concentration of electrolyte, it's very difficult to balance the charge. You have to pull further out into, away from the electrode to effectively balance that charge. So the field actually can drag on like a very long distance, sort of say, relatively speaking. When you have regular like 0.1 molar electrolyte, then it's very easy to balance the charge of like 1 volt or 2 volts or something like that. It's very easy to do that. You end up getting this very narrow region where like, okay, all the field strength is contained to this very small region. But if you have a very low concentration, like 0.001 or even lower, the field extends way out into solution and is very weak. So that explains the thickness of the double layer. So yeah, Wang, that's it. Let's see. He has a bunch of
They
comments
made you
here.
talk about electrochemical potential.
It made me talk about
I'm so
electrochemical
sorry.
potential. I know.
I
did not want to.
It's been a tough day.
It's been a very, very tough day. He has, what is it? He has one question back here, and then we'll talk to, let's see.
Mhm.
I'm not clear, how does a voltmeter work? Why things like SAM not affect the measurement of potential applied? We have a feedback loop which measure the potential difference between working between reference and working, right? So wait, so let me just see. Why things like the SAM not affect the measured potential that's applied? So the so the so the potential that's applied, let's say it's like 1 volt. And then when you added the self-assembled monolayer, you simply added a resistive element, and that resistive element creates like an IR drop. But this is a but this is like, oh, this is, let me delete this. This is just like a kind of a math problem, if you will, an Ohm's law problem. If you have a power source, like a battery or something, and then you have 2 resistors, I can add as many resistors as I want. Let's say this is 8 volts, and then I have 3 like 3 ohms here, and I have like 5 ohms here. The voltage across this is 8 ohms. I think I get like 1 amp, right? There's like 1 amp of current that will flow through this entire thing. So that means there's like a voltage drop across here. That's 3 volts. And there's a voltage drop across here. That's 5 volts. But the voltage itself is still 8. It's still whatever is applied. So I could keep adding resistors here, and maybe that changes, like, that'll change like the current, but like the voltage, the total sum of the voltage, no matter how many elements I put between here, is going to be, it's going to sum to 8 or whatever my value is. So if you add a thiol here, this is going to change this ratio around a bit, but it's still going to be 8 at the end of the day. So hopefully that makes sense.
The overall, that's what your potentiostat's telling you.
Yes,
that's why,
what your potentiostat's
and that's
telling
why your surface potential is not what you think it is,
Yeah.
because all the other things are there eating up potential along the way.
Mhm.
That's why IR drop is a bad thing.
Mhm.
A lot of times.
And you need IR compensation.
Exactly. All right, we are chugging along here. I see we have a lot of questions. The next question was about spectroscopy stuff, so you'll probably have to answer that. But Alex had a question, not you, another Alex had a question. Can you please explain how the potential of zero charge is usually measured by electrolytes and alkaline solution? What happened to my computer? There it goes.
There it goes. Okay.
I think I'm okay. Hope I'm okay. Hopefully everybody's still here.
Yeah, I think people are still here.
I think the power just
flickered
out for a second. Yeah. Honestly, it's a pretty simple answer. Generally speaking, what you're doing is, just as we described the electrometer, we were just talking just briefly a moment ago about the measurement between the sense lines of a potentiostat or a voltmeter, that voltage or whatever. Essentially what it's doing, potential of zero charge. Oh, sorry, I was thinking zero current. Now I'm I was heading down a thing of zero current, OCP, very simply, but now you're talking about zero charge. Zero charge.
I've heard about like the potential of zero charge. I honestly don't know enough about it. I'd have to learn more about it.
I mean, charge is the integration of current over time. So it almost feels to me like potential of zero charge is dependent on how much time has gone by and how much current is passing.
Well, it's supposed to be, I think it's supposed to be like what is the potential, like if you set the potential to like 1 or something like that, you're adjusting or charging the double layer, or when you've seen situations where like at 0 volts there is it's the current is not 0,
right?
Some background process is happening.
Yep.
So then if that's the case, what is the potential where you get, quote, 0 current, which should be the OCP, but yeah, I don't know. I feel like potential of zero charge also has something to do with like pH that I don't know enough about.
Yeah, all I was thinking was OCP, but yeah, zero charge. Yeah, that might be a slightly different phenomenon that we'll have to leave. I'm not sure I know the best answer to that. That might be a process that's more specific to something else, like you said, and I don't know.
Yeah.
So we'll have to leave it there. I'm not sure I can answer that. I mean, there's
I'll make a note about it.
This follow-up question here was, what's the difference between, I guess, potential of zero charge and potential of zero total charge? That's similar sort of a thing here. I suppose there's something about this. I'd have to look into it a little bit. It might be simple enough for us to kind of grasp, but
I haven't studied it.
Yeah,
so
that
I don't know.
specifically
I
is
haven't
a
read about it.
quantity I'm not really quite sure about, to be honest. But Sonu did have a follow-up here, I think, just about the band gap and things like that, basically asking, can I calculate electron mobility using spectroelectrochemistry setup that you have, our spectroelectrochemistry setup? So thank you for that. Can you calculate electron mobility?
I don't
I
know what
don't
that is.
think so. Electron mobility?
I don't know what electron mobility
I mean,
is.
we talk about like mobility of like ions, like there's, a lot of times you're looking those up. They're like usually tabulated values, but like ionic mobility, like different solvated salts have different like mobilities or speeds. And so you have like, there's some calculations that are like that. Those aren't totally electrochemical, I suppose. They're more like just properties of electrolyte.
Solid state physics.
Yeah.
How quickly an electron can move through a metal or semiconductor when pushed or pulled by an electric field.
Yeah, I don't know that there's a way with the spectroelectrochemistry to get that. I mean, get that particular measurement, or at least if there is, I'm not aware of it, to be honest.
Conductivity is proportional to the product of mobility and carrier concentration. Okay.
Yeah, we'd have to look into this a little as well.
I
don't know of a way to do this. I don't know if like UV vis spectroscopy gives you information that you can correlate with electron mobility. I don't know.
Yeah, I don't
think
so. Not for semiconductors. I don't know.
I think we'll have to move on. I suppose it. I think perhaps not, but we might have to just move on because I'm not sure.
Yeah,
to be honest.
So sure how to do that.
Samarash has a next question regarding EIS. If there's two humps appeared in semicircle section, what could the reason behind that be? Well, first of all, my quick response is do Kramers-Kronig, because if you have like a semicircle and it appears misshapen, it's usually one of two things. It means if it's a correct, like if it's a phenomenon chemically, it means you probably have two charge transfer processes of some sort, and they have similar time constants. Because you'd have like a multi-hump semicircle, or or almost two semicircles that are almost meshing into one, so something like that. But do Kramers-Kronig on your results, because sometimes that could just be error. It should be one semicircle or something, but there's some drift or issue with the data that's leading you to have misshapen plots. So do Kramers-Kronig to make sure. But generally speaking, the amount of semicircles or humps you'll see in a Nyquist plot is indicative of the number of processes that are occurring therein. So that's kind of how I would, I guess, sum that up. Okay.
I think there's a question you answered. You talked about this earlier. It's from M13N. He said, "Can you tell me if I need binder for GCE to immobilize my material, and if so, what kind of binder to make a better binder DLS
binder? I'm not does better.
Does better like nafion or any other."
Yeah. So the very first thing I talked about in this YouTube live stream we are on was related to a question someone else had asked about drop casting, basically, which is what you're talking about. So very briefly, nafion works as a binder. Yes, you do need a binder. It acts like a glue to keep your material immobilized on the glassy carbon electrode. And I talked at pretty decent length about some of the strategies for drop casting. So I will refer you to about 90 minutes ago. So right around, there's timestamps, but it's probably at the 6 to 7 minute mark of this live stream. Please whenever. Now you can ignore me what I'm saying now and go back in time, or do it later. But I talked a lot about drop casting and some things, especially with respect to nafion suspension. So I hope that you can go and listen to that part. That will probably address your question to a very large degree.
Mhm.
All right. Aniruddha has a question. During OER LSV, there is formation of pre-oxidation peaks. OER LSV, okay. Do these peaks occur due to diffusion control reaction or due to the surface species depletion by converting to a higher oxidation state? So I think it depends on what you're studying, for instance, but it could be the last thing that you said. So it is in particular, if you're using alkaline media, it is pretty common for alkaline electrocatalysts to themselves oxidize prior to catalysis of whatever you're studying, whether it's oxidation of some species or it's the oxygen evolution reaction. It is rather common for alkaline electrocatalysts to themselves oxidize to a higher state. That is something that can happen. Now, if it's not alkaline and it's something else, this may not apply, but that is certainly a possibility, I will say. And otherwise, if you have pre-oxidation peaks and it's not the oxidation of the catalyst itself or something like that, I guess I don't know exactly what it might be, to be honest. It could be oxidation of a different species in solution. You could have some other processes occurring, some other auxiliary or side processes. It's a little hard to tell, I would say, but I guess it is definitely possible that the oxidation of the catalyst itself is a pretty common observation at elevated potentials, for sure. And frankly, it's one of the things that's tricky at times. Like you're trying to just do OER, but the catalyst itself has its own thing going on. It's tough,
Mhm.
right? Because it's higher potentials to get oxygen evolution. So it can be tough.
The question from Samarish, he's asking from GCD, if I want to calculate gravimetric capacitance, whether it is mandatory to deduct potential drop, and if do that, then during energy density calculation, what should be the potential window?
No, you don't deduct potential drop. The gravimetric capacitance is just another way of saying that is the mass specific capacity. So like milliamp hours per gram, that's what you would say. I don't even know if I understand the question, because the calculation of the gravimetric capacity does not involve potential at all. Actually, it's let me draw. So, and correct me if you're referring to something else and I'm misunderstanding your question, which is absolutely a possibility. But if you have a charge discharge experiment, for example, right? This is voltage on this axis, and let's just say this is time. That's really what it is. Okay, and it starts at 4 volts, and you're gonna discharge it to 3 volts. Okay, what you often get is there's a drop in the potential, right? And then it will do this, and then it looks like the polarization curve. So coincidentally, they're all the same thing. But basically, what you're doing is you have a applied current. So it might be, let's just say, minus 500 milliamps, because it's a discharge. You could just say 500 milliamps of discharge current or minus 500, whatever, it doesn't matter. Okay, so you're discharging at 500 milliamps, and this lasted 1 hour, right? Well, your capacity is 500 milliamp hours. Now, the gravimetric capacity, if you had 10 milligrams of catalyst, is 500 milliamp hours divided by 10 milligrams. So your gravimetric capacity is 50 milliamp hours per gram. That's a gram, 10 grams, whatever. Forget the prefix. Make it simple. Milliamp hours per gram, right? Hope you understand. I didn't mean to put milligrams and make it complicated. This is just the unit that everybody uses. My point being is that this has nothing to do with voltage insofar, other than that it hit this, it was at 4 and it went to 3. Now there's a voltage drop associated with basically ohmic losses or something like that, which is why when you stop discharging, the voltage would like recover or whatever. But that doesn't really matter for this calculation. And again, if you're talking about something else, that's then you can let me know or correct me if I'm wrong. But effectively, you're looking at the time it takes at a certain applied current to get from one voltage to the other. That's just how this works, and that time times the current applied is the capacity, and then divided by the mass of whatever you have working for you is the gravimetric capacity. You wouldn't correct that for voltage, basically. Like you wouldn't, I don't know, maybe you're talking about like, well, there's a voltage drop, so I should really go to, down to 2.9 volts because I had, 0.1 volts of loss or something. You wouldn't do that. It's not a wise idea. You could discharge, you could overcharge your battery, things like that. As far as I'm aware, that's not really a practice. So the potential window, this is a tricky thing, right? Technically, you are sort of correct if you say, for example, well, my potential window is 3 to 4, but every time I stop, it relaxes a little above or a little below, depending which direction I was going. And it's like, well, my potential window, it's the similar conversation we had before, where like the ohmic losses impact the actual voltage of my system. And that's true. It's true in a battery. It's true almost anywhere. But we don't do that for a battery, probably for the simple reason that if we try to correct for that by like going below or above the charge limit or the discharge limit, because we know that some of it's ohmic loss, you may inadvertently severely damage your battery or kill its lifespan. It's a very bad idea with a battery. Now, with something else, maybe it's not as big of a deal. But with a battery, if you over discharge it or you overcharge it, you could destroy the SEI, which causes thermal runaway to commence. You could cause all kinds of problems. I don't recommend it. So there may be instances where people have done something like this, but as a general rule, I would not suggest any kind of voltage correction when you're doing these kinds of measurements with a battery. You just have to take your ohmic losses and deal with it. This is why people make batteries in tightly packed coin cells and cylindrical cells and everything, because it really does minimize the ohmic drop to a pretty dramatic extent. Like the ohmic IR drop in resistance or impedance of a battery, a well-made battery, can be milliohms or even microohms if it's really crazily well made. And so, yeah, you'll have some ohmic drop, mainly because the current is so high, right? I times R. R is really low, but I is high. So, okay, there's a little bit of, millivolts or of loss or something like that. But it's not something that you want to correct for, because you could really, it's actually a safety thing, not so much necessarily of like, well, I want to make sure I'm exactly at 3 volts or exactly at 4 volts. It's like, okay, well, if you mess that up a little bit, your battery's dead. That's a problem. So that's my advice on that. If I've understood your question correctly, I guess. So.
All right. We have a lot of questions and not too much time, but let's see. We have a question. In EIS with 2 semicircles, what is second capacitance other than double layer capacitance?
It's a great question.
Yeah.
So generally speaking, if you have the most common, I would propose reason you have 2 semicircles in an aqueous plot is because you have some sort of a film, some sort of a substrate in a film interaction that is usually represented by the higher frequency leftmost semicircle. And then you have another semicircle, and that is representative of the charge transfer process of interest. Okay. And so typically what we do is the second semicircle would actually be attributed to the double layer capacitance along with the charge transfer resistance, which is the width of that semicircle. The first semicircle has its own representative resistance, which would be like the resistance of the like film formation or the resistance of the film itself, something like that. And then the capacitance would be effectively where we would say it's like the capacitance of the film. Now, does the film make some kind of double layer itself, like separate double layer? There's a lot of open questions here. I don't know that I have the answer to perfectly well, but it's sort of like you can think of it that way, that the film or the substrate in the film or the in a battery, in the case of a battery, like you'll have a semicircle for the SEI, solid electrolyte interface. And so it would be the capacitance of the SEI, basically. Now, how is that different and distinct from the double layer capacitance? These are all great questions. I wish someone could answer them. Maybe I'll ask someone about electrochemistry someday. I don't know. Yeah, there's a lot of open questions here, but usually that's what the interpretation is in the literature. I do find that somewhat lacking, because it's like, how are these different capacitors all set up and distinct from one another? It's a little tricky to like, even for me to like, to wrap my head around. Like we just, Alex you just drew all this stuff with like the inner Helmholtz plane, and there's a capacitor there, and it's like, okay, well now I have an SEI or a film. Is that like out here or closer to it? Like, how is that? I have no idea. I really don't know. Maybe it's like there's multiple layers, and that there's a capacitance at each layer. That could be a way to interpret it. But that's what you'll see reported in the literature, to the best of my knowledge. It's like, it's the film capacitance, and then there's the double layer capacitance. Something like that would be my best answer for you, I guess. But great question.
Yeah. Anytime you have charge separation, you have capacitance in some way.
Yeah.
So you have to think about it that way.
Yeah.
Hob G has a question. Now, generally in CV, you expect the peak current to be higher at tighter, high concentration electrical double layer, or at a tighter electrochemical double layer, which is a higher electrolyte concentration. So let me I guess I'll phrase it this way. When you have a higher electrolyte concentration, it makes two changes. It decreases the solution resistance, and it increases, yes, it makes a tighter electrical double layer. It is more so the fact that you have a less solution resistance that's going to give you a higher peak current than it's the fact that the double layer is like tighter. That's going to give you a higher like a higher peak current, sort of say, if that makes sense. So yeah, you may observe as the solution as you add more electrolyte to your system, your solution resistance decreases and your peak current goes higher. Of course, there will be a limit to that. You can't, if you go from 0.1 molar to 1 molar and the resistance doesn't change that much because it's already like an aqueous solution, it's already very conductive, you're really not going to see that big of a difference in like peak current in your CV. So hopefully that kind of makes sense. We got approximately 15 minutes left, and let's
crank through this,
and we'll get through as many questions as we can. I can tell you're getting the next one up and ready. The next question is from Alex, who's asking, sorry, we couldn't answer your previous question, but could you please explain what Kramers-Kronig is?
Certainly. I can explain what Kramers-Kronig is. Kramers-Kronig is, in short, an analytical technique for impedance data that judges its validity. And it is designed to answer the question, is my data valid? And the answering that question by validity, we are referring to 3 different conditions. I know 2 of these this is part of my webinar, so that's why 2 of these look faded out. That's on purpose. The conditions of validity are stability, causality, and linearity. See, like those animations? Those are manual animations. So linearity, causality, and stability are the 3 conditions for valid impedance. And Kramers-Kronig, these are mathematical representations. So they're right. These are them. It's basically a calculation of the frequency-dependent real impedance as a function of the imaginary impedance, and the frequency-dependent imaginary impedance as a function of the real impedance. They're just mathematical transforms, and effectively, if they are satisfied, if the equations work out, your data is valid, and if they don't, it doesn't work out. What we do is effectively all the things that are circled here are the problems with this. These are infinite integrals Basically, it's really impossible to evaluate these numerically, or it's really difficult to do so. So what we do instead is we apply this circuit here, this representative circuit that just has like everything, resistors, capacitors, inductors, and void elements. We apply this to our data, and we use the idea that this example circuit satisfies these equations necessarily. And this example circuit with infinite amounts of elements to make it as ideal as possible fits our data. And so if this circuit fits our data and this circuit fits Kramers-Kronig, then our circuit fits Kramers-Kronig. And finally, if our circuit fits Kramers-Kronig, it's valid. Or our data, basically, right? So it's a way to, is technically indirectly a way to answer the question, is my EIS data valid? And that's what the Kramers-Kronig relations are. Now, practically, the software does this. Our software does this for you automatically. And I could show you that, I suppose. So get some data really quickly here, and I'll show you the Kramers-Kronig done in our software quickly, so we can move on. And we have like 1.5 million questions still to answer. So this is these are some data sets. Here's drifting. This is data that's pretty bad on purpose. See, the points here at the end are all kind of wonky and crazy. So when I do Kramers-Kronig on it, you'll see that it's trying to fit it. And you'd think that it would fit everything because there's like an infinite amount of void elements and RQ and RC and everything. And it should fit everything. And the reality is, well, if the data is bad, it doesn't fit it. Looks pretty bad. It's kind of all over the place. And that's an indication, well, at least these data points are not accurate. And it's like, well, I can get rid of some of the bad points and maybe my data will fit a little better. And it starts to fit a little bit better if I just kind of get rid of some of the low points. So there's some things you can do. But in any case, that's what Kramers-Kronig is. And I will leave it there for now.
The next question is, I want to do an EIS to a solid electrolyte gas sensor and metal oxide semiconductor, tin oxide. Any special considerations? I am new to EIS. Well, they're solid state, so push the electrodes and stuff, like squeeze them next to each other. I don't know. I don't do enough solid state EIS.
Solid electrolyte and a metal oxide semiconductor. Yeah, they're going to have to be touching.
Yeah,
most
they
probably.
have to touch stuff.
Without a liquid electrolyte to balance the charge, they have to be touching each other because impedance or any other electrochemical experiment requires that there's charge balance, which means that the electrons and the electricity and the voltage difference causes a flow of electrons to go through your potentiostat that's measuring everything. And so there has to be a concurrent movement of charge in this cell or the system, which is usually ions, right? And that's convenient. That's why we use electrolyte, because it has positive and negative ions, and they move around and swim around the system, and the negatives go over here, and the positives go over there, and everybody's happy. With a solid system, there has to be charge movement. And so there's no liquid bath to like make that convenient. So I suppose they probably have to be pressed together pretty close. And then other than that, special considerations is that generally speaking, I don't have a lot of experience myself with solid state systems, but I do know that they tend to lend themselves to high frequencies. You may need to find an instrument that can go to megahertz or even higher megahertz, 2, 3, 4 megahertz, which is very fast. It's tricky because the accuracy at high frequencies is severely diminished. So you'll have to repeat the experiment a lot to try to sort of weed out signal from noise, if you know what I mean. You'll do the experiment 5 times and get 6 results. So it's hard, especially with solid state systems, I believe. So that's hopefully that's a few little tidbits of information. Other than that, it's you'll have to some trial and error for sure.
Yeah. So next question, I think it's a follow-up question. Follow-up question is my first question. How to explain the occurrence of a peak like we do in the Cottrell equation in diffusion-controlled reactions?
Occurrence of a peak.
Are you referring to
an EIS peak or? Because the first question
Oh.
was about EIS humps, I think.
Well, he had a even more original question. He said he's had like a during LSV
yeah, you're right.
So
I didn't see that first one. Yeah, I forgot about it.
yeah.
Oh, I see.
Well,
yeah, right.
so I'm just wondering whether or not you're talking about
Occurrence of a peak like we do with Cottrell equation.
So the occurrence of so when you have the Cottrell equation with like chronoamperometry, you have something that looks like this, and I don't know if this is exactly what you're talking about. You're trying to, you have time, and you have current, and then nothing's happening. You get a spike. That's your peak, and then you have a slow decay. And this is your Cottrell response. Like this is what you normally get. This peak is associated with charging of the electrical double layer, as well as some Faradaic reactions initially occurring because you're applying a very high potential. You're going from like 0 to, I don't know, let's say 2 volts, right? You got lots of, it's going to have a lot of current very quickly, reaching this point. And all these processes are going to happen. And then you're going to get the mass transport, diffusion controlled current response. So I think, is that the peak that you're trying to explain? I'm not 100% sure. He says, yes, about pre-oxidation peak. So that's what that's from. If you're doing this in LSV, here's a thing I would keep an eye on. This is something in our software, so I can't speak for what you might be going through exactly, but go to software. So in our software, if I'm doing a let's do LSV, linear sweep voltammetry, this is all the basic parameters that you would have. But under the advanced tab, there's something called an induction period. And the induction period is a time when nothing is happening, like no data points are being collected. Because if you were to set this to like 0, then your potential just goes from like 0 to whatever very quickly, and then you get this like, yes, pre-oxidation peak. But you need some kind of like, but this induction period is like, okay, before we start collecting data, let's put the potential to like 0, set it there, let it sit. And then when when you set this to start at like 1,000 volts, or sorry, 1,000 millivolts, it's already at 1,000 millivolts for a little bit of time before it actually starts the experiment. And that way you don't start with this like weird pre-oxidation peak, or sometimes it's, you have to step up to create the electrochemical, the electrical, double layer.
Well, that's that right there. What you just said is part of the answer to your question. Why does peak appear due to oxidation of? So,
my question is, why does peak?
If you're asking about the peak in the Cottrell plot or the chronoamperometry, it's what you just the double layer. When you set a potential and you just measure the current response, you initially get that the peak, what looks like a peak, is spike of current when the formation of the double layer and some kinetic things, and then it decays due to mass transport. So I don't know if you were asking before about peaks. It seemed like cyclic voltammetry peaks or whatever, but he's just asking this as you were describing that peak, I think. And what you just said was that peak forms when you apply the potential.
Yeah. Like when you initially apply the potential, you get a spike in current.
Yeah, and to a very large degree, that's the setting up of the electrical double layer.
Yeah,
right, and kinetic things that are happening. So in the same way that I answered your question before, that sometimes, like in a cyclic in an LSV or a cyclic voltammogram, you'll have like a peak and then the OER or something like that. That peak that occurs in cyclic voltammetry could be the oxidation of the catalyst itself. Like I said, it might be. I don't know. In some systems, it can be. But if you're just doing chronoamperometry at some whatever, you'll always get a peak regardless of where you're at potential wise, because you're setting a double layer up. Then some of that peak, I guess you'd say, right, the spike of the current or whatever at the beginning of your chronoamperometry is the double layer setting up, and then and then also some kinetic processes. So you might have contributions from both, but you can't really differentiate very easily in the chronoamperometry that peak in current. Is that a Faradaic process happening, or just the double layer setting up, or both? You can't really differentiate that very easily.
Yeah.
So
hopefully that answers that. Okay, we got a question from Chandan, and he's asking, in OER experiments, I'm getting 10 milliamps at some overpotential, and then current density get down, and then it is getting up. So I am confused. Which overpotential should I report, as current density is reaching 10 milliamps twice?
yeah, I mean, you can report the first one because it's technically true, but you also probably need to answer and investigate why you have this behavior. The simplest answer is, well, if you scan or do a bunch of steps or something, right? And the current density goes, what are you doing? OER? OER. Yeah. So you should go up. This for me is positive.
Yeah.
For you, it's backwards, whatever. The potential is going up. It's up higher. The current reaches 10, and then it drops, and then it goes up again. It's like, there might be a reason for that. It might even be similar to what I just talked about. In a similar way, a lot of people do OER in alkaline systems, and a lot of alkaline catalysts themselves will oxidize. And so sometimes what you'll get is like a peak in the OER region. And sometimes that's the catalyst itself that oxidizes and has its weird process where there's chemical and electrochemical reactions mixed. This can happen in alkaline media, and then the OER happens more firmly or something. And so if you're, I don't know what people routinely report, I guess is my point. Like, do people just sort of, it feels like cheating, right? It's like, well, it happens at, 1.4 volts, it hits 10 milliamps. And then then it goes down. And then at 1.55, it hits 10 again on its way up, further. Well, should I report 1.4 or 1.55? Well, 1.4 is not lying, but it's like not the last one. So you feel like it's wrong. Look, I don't know what people routinely report. I would assume that people try to produce a smooth curve, and so it's clear there's only one place that it hits that current density. My impression is you would report the first one because it's favorable for you and it's technically true, but then you would show, like ethical, like reporting of your data would show that it reverses, there's a peak or something like that, and you could discuss like, there's some other phenomenon happening. You'd have to try to figure out what that is. As I said, maybe it's the catalyst oxidizing itself. But you could discuss that, like, oh, well, at 1.4 volts, I hit 10 milliamp per centimeter squared. Then there was this behavior occurring, and that's because of possibly X, Y, or Z. But we report this potential formally as this overpotential. You would sort of cover all your bases by discussing the behavior that you're observing. That would be my, I don't know, my advice, I suppose. I think we have a couple questions to try to get through.
Yeah.
If you want here. Abhinav has asked about a CHI potentiostat. So I'm not a CHI. We're Pine.
Yeah.
Can't speak, but essentially you're saying there's 4 leads. 3 of them you're using as 3 electrode system. The last one you don't know about. You think it's for working sense. So I suspect if you are successfully doing 3 electrode experiments and this lead is disconnected, it is not the working sense.
Yeah.
In fact, I'm 100% positive that if you are conducting 3 electrode experiments and this lead is disconnected and your experiments are not garbage, that is not the working sense. It's probably the countersense, if they have a countersense. I have no idea.
Or it's actually a simple rag had they like mentioned it could be the ground.
Or it's the ground.
Or the DC common of the instrument.
Yep.
Which is usually used for if you just need to ground the potentiostat
sometimes
to
it helps reduce
noise.
Yeah,
It lowers
it doesn't always. Sometimes it does.
Yeah, sometimes it does.
I can't speak too much more to that. You'll have to contact CHI. I don't know their system. But generally speaking, when you have a 3 electrode experiment, working drive and working sense must be connected to the working electrode. In some potentiostats, maybe CHI does this, I don't know. Those are one lead. They have it connected together. Most modern potentiostats have 2 separate leads for working sense and working drive, but those need to be connected to the working electrode and then counter and reference obviously go to those respective ones. And then the only other leads that typically exist, if you have a bipotentiostat, there's another set of working. It'll have a ground lead or DC common or chassis ground, something like that, or a countersense sometimes in very rare instances. We'll have a countersense. But so there's the best we can do for you in that respect to your CH. And then I think the last thing I'll do is answer Simple Rog's question here. So in galvanostatic charge discharge, if the discharge curve after some time becomes parallel to the x-axis, should we consider that time or subtract it while calculating capacity? Why would you subtract it? If it becomes parallel to the x-axis, I guess if it's parallel to the x-axis,
I'm saying the voltage is just staying
the voltage is staying the same
over time.
Yeah, that's a bad sign. If you end up in a situation, for example, where you are discharging something, this one, right? And let's say that let's just say this bottom is your cutoff, like V lower, whatever, and this is your V upper, whatever. That's not supposed to be a mu. I don't know. V upper, whatever. Okay. And your discharge, and you get like, whatever. I don't know. Maybe you have some thing where it's like just doing this, and it doesn't ever seem to it doesn't ever cross zero. Right? It just keeps going out forever, whatever. Something is bad. Something wrong is happening. It needs to get to your lower limit. You need to have a situation where your discharge hits your lower limit, one way or the other. What's probably happening is you're just ripping apart electrolyte endlessly. And that's not, so you can't just say, well, here, because, well, how do you know? How do you know where it started really ripping apart the electrolyte? And how much of this was this part fine, but this part here was, bad because that's electrolyte ripping up? Or is this part good? How much of this was electrolyte ripping up? Like this part all is probably fine. Okay, great. But where did the electrolytes start getting destroyed? Contributing to artificial capacity, because this is time right here, right? This is time. And so as the longer it lasts, the better its capacity you're going to report. Well, how do you know? Is this where the capacity stopped for real? That's why you have a cutoff voltage. You have to have a cutoff voltage. And so one of two things is true. Your material's poor, it's ripping apart the electrolyte, or you applied an improper lower voltage cutoff. I do not suggest artificially assuming you should just stop it somewhere. Something has probably gone wrong with your experiment. So that's something to look out for. Okay. We did not get to all this saved questions, but we got to a couple.
Yeah, we got to a couple.
I feel
That's pretty good.
We have this thing on DRT. I'll try to answer next week. There was someone you were communicating with on LinkedIn, I think, who had some questions about distribution of relaxation times. I have a whole answer to that I will not talk about today because it's already past time. As is always the case. We get swamped. You guys are great. Yeah, you guys are great. We appreciate all the questions. And we just don't have voice boxes for 9-hour sessions. It's just not,
Yeah, but continue to ask questions. Hey, the sooner you get the question to us, we'll try our best to answer it before it actually starts, and prioritize your question.
Exactly. And I guess with that, we will call it a day, a week, a weekend, everything. And I always do this. It's like, we're nothing. It's just April. We're good. All right. Well, we will be here next week.
Yes, we'll be here next week.
And I hope everybody has a great rest of your Friday, or if your Friday's already over and it's a weekend, have a good weekend. Have a good week, everybody. And I guess for any of you who are in the United States, on next Wednesday, there's a battery show in Atlanta, and I will be there. I don't have a booth, but I'll be walking around the expo floor probably most of the day.
Nice.
So if anybody's around and you notice me, come say hi, I guess. I doubt that'll happen, but just throwing it out there. So anyway, good to see everybody. Well, I didn't see anybody. I saw you.
Oh, yeah.
Good to talk with everybody. Thank you for the questions.
Good to type with everybody.
And we talked.
We talked.
But anyway, we will see y'all next week. Have a good one.
Bye.